Hi to all. Today's topic is induced EMF. That is motional EMF formula I am going to derive. Then topic is motional EMF. Motional EMF. This is our topic. Motional EMF. Then in this what I am going to derive? Right? I am going to derive the induced EMF. Okay. Induced EMF formula I am going to derive in certain special situation, that is, for example, this is a conductor. This is a conductor. Means it is a wire. It is a wire. Okay. Without insulation, and now it is bent in the shape of rectangle. It is placed in the uniform magnetic field. The magnetic field is inward. The magnetic field is inward. It is uniform. Now take another current carrying conductor. This is some wire. This is a PQ conductor. This is the P and this is Q. It is a conductor, and this conductor is moved on the rectangular frame with velocity v in the magnetic field of induction B. What happening at here? This is a conductor. This conductor is moving with velocity v in the magnetic field of induction B. Then our question is that then when we move this conductor with certain velocity, then actually like this happens. This is the situation. Now for example, the length of the conductor is L and this distance of the conductor from one end is x. Now when the conductor moves with certain velocity, after some time the conductor goes to other location, that is, for example, the conductor goes to here. This is the new location of the conductor. This is the new location of the conductor, and the conductor takes some displacement, that is the dx. In this case, what happening when the conductor goes with certain velocity and it takes certain displacement, during this what happening, the area of the loop is increasing. When the conductor is moving right side, then its area is increases. When it's this area, when the conductor is at here, the loop area is this much. When the conductor goes right side, the loop area is increasing. That means when the loop area is increasing, means flux will be increases, because the flux link with the loop formula is BA cos theta. Actually what happening at here, this is a rectangular loop. Okay, rectangular loop we are having, but over this rectangle here, this conductor is movable. When it will move right side, the distance will be increases. Then automatically area is increases, the flux changes. When the flux link with the loop changes, at that moment in this EMF and current will be induced across the conductor. That EMF formula I am going to derive, right? And it was very simple and very important for the 3 marks, and it's based on these problems also very important, and you listen very carefully. I am going to derive, I am going to explain its derivation part, right? And for that, what I have to do first? First I can find out the flux link with the loop. Okay, right. L is the length of the conductor. A conductor PQ of length L moves with velocity v in the magnetic field, of induction B, as shown in figure, right? As shown in figure. The flux link with the loop, what happens in the figure? Flux link with the loop, right? What is the flux link with the loop? Right, that is the phi is equal to, we write as BA cos theta. This is the flux link with the loop, right? What is B here? B is the magnetic induction, A is the area of the loop. But here we can write one thing, that B bar parallel to A bar. Why? What is B bar? B bar is the magnetic field. Magnetic field is inward into the paper. Area vector is this is the surface area, right? Area vector is perpendicular to surface. It is also inward. The both are parallel to each other, right? Area is, for example, this is the surface. Okay, this is the surface. Area vector either outward or inward will be there. Okay, if you take the outward, then the B and A are opposite direction. Then you take the theta is 180. If you take inward, then B and A are parallel, then theta is 0. Then we write as theta is 0, right? Theta 0. But area is what? Area of loop. Area of loop from the figure we write as ALX, length into breadth. This is the length of the conductor L, distance from one end is x, length into breadth. This we substitute in above equation, right? Then flux is equal to magnetic flux, we will get as, yes, what you will get the magnetic flux, can you tell? Yes, that you will get as BA, A is LX, BA, A is LX, length into breadth, into cos 0 value is 1, cos 0. Finally, we are getting the magnetic flux as BLX, this is equation 1. Okay, then I want the induced EMF. What is the induced EMF across the conductor? Induced EMF across conductor PQ. Across conductor PQ, how much induced EMF generates? That is according to Faraday's law we write. According to Faraday's second law. What we write? That is induced EMF is equal to negative rate of change of magnetic flux minus d phi by dt. This you substitute here, minus d by dt of phi we write as BLX. Okay? Right, in this induced EMF is equal to minus BL into, BL is a constant, remaining we write as dx by dt. What is dx? Dx is the displacement of the conductor in time dt. Then dx by dt gives the velocity of the conductor. Then induced EMF we write as minus BLV. Okay, where this is the dx by dt gives the velocity. Right, and this is the formula for the induced EMF. The magnitude of induced EMF, magnitude of induced EMF E is equal to, we will get as BLV. Okay, right. This is the situation, and this is, we can take it as equation 2, right? And this is very important derivation, and it was very easy, and you take the screenshot and note it. Okay, if you have any doubt you can ask me. Okay, then after that I will rub it and then I will continue. Okay, we derived the induced EMF formula as BLV. Induced EMF formula is BLV. Then, for example, if the some note point I am going to give, note, right? Note. Induced current I want. What is the induced current in this loop? Okay, induced current. Induced current in above case I want. Okay, in above case. What is the induced current in above case? Yes, how to get the current? Actually, this is a conductor PQ. This conductor PQ, we are moving in the magnetic field with velocity V. Right, that conductor length is L. that conductor length is L. When you move this conductor, right, its length is L in the magnetic field of induction B. Now across this conductor, right, EMF will be generated. Induced EMF across PQ conductor is BLV. Now some current flows in this loop, right? What is the, if induced current I want in the loop, current is equal to be write as effective EMF by effective resistance. Effective EMF by effective resistance. Effective resistance. Then what is the effective EMF? That is E. By effective resistance is R. Okay, this loop resistance we can consider as R. Then we write as I is equal to BLV by R. This is the current formula. Then how to know the direction of induced current? This is induced current, means developed current. Without battery in this current will be induced, right? This is the induced current. Induced current direction I want. If you want to know the direction of induced current, then you have to use some rule, that is the Fleming right hand rule. Fleming right hand rule. That Fleming right hand rule is useful to know the direction of induced current. Fleming right hand rule. Fleming right hand rule. Fleming right hand rule. What is the use of this rule? Okay, before going to this rule, actually I am telling that this is a, if this is a conductor, right, this is a magnetic field. If the conductor moves, what is Kepler in this? R is the resistance of the loop. Resistance of loop. Okay, if this conductor moves with certain velocity, L length of conductor moves with certain velocity, right? Induced EMF across this conductor, induced EMF across this conductor formula is BLV. Then this formula is applicable, right? Induced EMF E is equal to be write as BLV. This formula, the above formula is applicable when L bar perpendicular to B and perpendicular to V. If these conditions satisfied, then only this formula is applicable. That means B, L, V, the three are perpendicular. Look at here, L is like this there, V is like this there, perpendicular. B is inward, all are perpendicular, right? In this case only we will use. Otherwise we use induced EMF, right? In general, that is E is equal to L bar dot V bar cross B bar. This is the formula. L bar dot V bar cross B bar, that we can use in any other case. Okay, right? And now, what is the Fleming right hand rule? It is used to know the direction of induced current. What is the use of this? It is used to know the direction of induced current. It is used to know the direction of induced current. Whenever the flux link with a loop changes, in that current will be induces, EMF induces. To know the direction of the current, we are using the Fleming right hand rule. Then what is the Fleming right hand rule? That is, it was very simple. The Fleming left hand rule also we learned. What is the Fleming left hand rule? You have to stretch the left hand forefinger, central finger, thumb in such a way that they are mutually perpendicular to each other. Right? Then this forefinger indicates the direction of the magnetic field, central finger indicates the current, thumb indicates the force. That means this Fleming left hand rule useful to know the direction of the force on current carrying conductor. force on current carrying conductor in the magnetic field. If you place any current carrying wire in the magnetic field, it will experiences the force. To know the direction of the force, we use the Fleming left hand rule. That means if the forefinger is adjusted in the direction of the field and the central finger adjusted in the direction of the current, then the thumb gives the direction of the force. But we are discussing the Fleming right hand rule. Right? Fleming right hand rule is that stretch the forefinger, central finger, thumb of your right hand perpendicular to each other. This is useful to know the direction of induced current. Then how it will give the direction of induced current? Then look at here, you adjust the forefinger in the direction of the magnetic field. Adjust the thumb in the direction of motion of conductor. Adjust the forefinger in the direction of the field and thumb in the direction of the motion of conductor. Then the central finger indicates the direction of induced current. This is Fleming right hand rule. Okay? Stretch what? Forefinger, comma, central finger and thumb of right hand in such a way they are mutually perpendicular to each other. Three fingers should be perpendicular to each other. Okay? And if thumb indicates if forefinger indicates magnetic field, comma, thumb indicates motion of conductor, then central finger indicates direction of induced current. Okay? Right. Let us see here in this what we are giving. Right. This is the statement. And now let us see here, I will write in simple format, that is the forefinger you have to adjust in the direction of magnetic field. Right? Forefinger in the direction of magnetic field and thumb in the direction of motion of conductor. And then last one, which one? Central finger. What it will give? It will give the automatically direction of induced current. This is our Fleming left hand rule. Okay? Fleming left hand rule. Now take the screenshot and note it. In this I will show the direction of induced current, how it will be there, right? Based on the Fleming left hand rule. Now you take the screenshot and note it every point. Okay, let us see the example, the same example whatever that we are discussing. The Fleming left hand rule application I am going to explain. For example, this is a conductor, already we know that we are taking, this is a PQ conductor, right? PQ conductor. It is moving with velocity V in the magnetic field of induction B, and the length of the conductor is L. And now here it is moving in the magnetic field. This is the magnetic field. Now I want the direction of induced current. In the loop. Actually, why current will be induced in this loop? already we discussed. When the conductor moves, area of the loop is increasing, right? And the conductor is moving in the magnetic field. That means the magnetic flux, when the area increases, the flux link with the loop changes. The change in flux induces the EMF or current in the loop. That means due to that, current will be induced according to Faraday's law. Now I want the direction of induced current. For that, what you have to do? You have to stretch your thumb, forefinger, central finger in such a way that they are mutually perpendicular to each other. We have to stretch in such a way that they are mutually perpendicular to each other. Adjust the forefinger in the direction of the magnetic field, thumb in the direction of the motion of the conductor. Then central finger automatically shows the direction of induced current. But while stretching, we stretch these three fingers in such a way that they are perpendicular to each other. But if you, for example, here if you see, the forefinger is the magnetic field, but the magnetic field is inward. Here it is the forefinger magnetic field. Right side it is showing. Inward means into the board. We have to rotate. We have to rotate your wrist, and you have to rotate your forearm. Okay, you have to rotate your elbow, but don't rotate the fingers, because fingers always, they should be mutually perpendicular to each other. Now adjust the forefinger in the direction of the magnetic field, that inward, and adjust the thumb in the direction of motion of conductor, right side. Then the current is downward, right? Current is downward. Look at here. Sorry, we have to use right hand, not left hand, to know the direction of induced current. To know the direction of induced current, we have to use the right hand, not left hand. Don't be confused, right? And look at here, this is the right hand. Then you have to adjust the forefinger in the direction of the magnetic field, right? In the direction of the magnetic field, and thumb should be motion of conductor. Then the current will be upward, it is showing. Look at here, thumb motion of conductor, right side, conductor velocity, right side, and forefinger field inward, and this central finger upward. Central finger indicates the direction of induced current, right? The induced current is upward. Induced current is upward. Like this the current flows. Like this the current flows. This is the direction of induced current. Then when induced current goes up, okay, this is the direction of induced current. How to find the direction of induced current according to Fleming right hand rule. Then when you know the direction of induced current, then if the PQ act as battery, it is equivalent to battery. If the effective resistance of this one is R, for example, this loop has effective resistance R. This is equivalent diagram I will draw. Okay, equivalent diagram. This is the conductor PQ. This conductor PQ will act as a battery, right? This conductor PQ behaves like a battery. Then which is high potential and which is low potential I want? Conductor PQ behaves like battery, right? And in this current is inducing, right? And EMF is inducing. Induced EMF across PQ is what? Induced EMF across PQ conductor is BLV, we know already, right? Induced EMF across PQ conductor is BLV. That means here conductor PQ behaves like battery. When it is behaves like battery, it should have positive and negative terminals. But one thing that, okay, if it is behaves like battery, inside the battery, when you take like this, okay, current outside flows from positive to negative, but inside of the cell it will goes from negative to positive. Here current is flowing from here to here, means this will act as negative potential and this will act as positive potential, right? Remember that. Why? Current flows from this PQ behaves like battery. Current in batteries flows from negative to positive. That's why P act as negative and Q act as positive. Okay, P is at low potential and Q is at a high potential. And now if it is, we draw the equivalent diagram. If it is the total resistance is R, here we write induced EMF across PQ conductor. Induced EMF, what we write? Across PQ is E is equal to, we write as BLV. Okay, the current flows upward. If the effect resistance of the loop, we can like this. This is the effect resistance, and this is the battery. We take it as negative terminal, and this is positive terminal. Then the current will flows like this. Okay, and then the current direction. This is the PQ. This is P and this is Q. This will behave like negative, right? That's why we wrote negative terminal, and this will behave like positive. That's why positive terminal. And the current flows from positive to negative from outside, right? Like this it will goes, and then like this it will goes. This is the direction of the current, and the induced EMF is equal to write as BLV, right? Induced EMF is equal to BLV. In this, the wire is, this conductor is moving in the magnetic field, right? The magnetic field is B. Magnetic field is B. Right? And if capital R effective resistance of loop, if capital R is the effective resistance, then what is the current in the loop? Yes, we know current in the loop. Current formula is induced EMF by resistance, that is BLV by R, where B is the magnetic induction, L is the length, and V is the velocity of conductor. This we already discussed it. Now, where we can apply this one, and I will explain with one problem. Okay, right, let us see here. I am going to rub this, and then after that I will explain the problem. Okay, let us go for the two problems. This one I can give the solution, and this one you have to try, right? And the same model problem, and it was very easy comparing with my problem. I am going to explain. A jet plane traveling west. Okay, for example, this side west is there. Jet plane is traveling towards the west like this. Okay. Now, for example, we can take north, south, east, west. For example, this is a jet plane. It is traveling in west direction with certain velocity. The wing span length is L, and now here this is the, for example, wing of the jet plane, and it is going like this. The jet plane is going like this, or like this it is going. Its length is like this there, and its velocity is like this there. Now it is moving in the earth magnetic field, right? Jet plane is moving in the earth magnetic field. Then what is the induced EMF across this wing of length, certain wing span of length 30 meters that they give? Right? What are the given data for this solution? Let us see here. It was very simple. A jet plane traveling west with velocity 450 meter per second. 450 meter per second. And if the horizontal component of earth magnetic field, that is BH, is given as 4 into 10 to the power of minus 4 at a Tesla, at an angle of dip denoted with 30 degree, then find the EMF induced across the span of length. Okay, this jet plane span, wing has length 30 meters. Across that, how much induced EMF generates? Actually, we know that the induced EMF will be generates when length and field and velocity, these three should be perpendicular. For example, this is the span. For example, this is sketch pen, we can take as the span, wing span, okay, wing, and it is moving right side like this, right? And length and velocity are perpendicular. Then they gave the horizontal component of the earth magnetic field also like this there. Vertical component is like this there. If you take the vertical component of the earth magnetic field, length is along this like this, and vertical component like this, vertical component of earth magnetic field, velocity like this, all are mutually perpendicular. But if you take the horizontal component, it is not perpendicular. Okay, and it is parallel to the velocity. Velocity horizontal component is along the horizontal, it is there, and velocity is also along the horizontal. Then induced EMF is 0 in that case. That's why in this case we have to take the vertical component, but they give the angle of dip. We know that, okay, BH is equal to tan delta is equal to BV by BH, you know, right? Tan delta is equal to, we know, angle of dip formula BV by BH. From this we write BV as BH into tan delta. We write, what is BH? BH they gave us what, 4 into BH value 4 into 10 to the power of minus 4 into tan delta. Tan delta is the tan 30. Tan 30 value, you know. Yes, what is the tan 30? Tan 45 is 1. Tan 30 is 1 by root 3. Then we write as 4 by root 3 into 10 to the power of minus 4 Tesla. Here we got the vertical component of the magnetic field, BV, vertical component, and span length, velocity perpendicular. Then induced EMF formula we will get as, okay, right, induced EMF formula is BLV, but here we take BV, vertical component of the field we have to take, because vertical component upward and length horizontal like this it will be there, and velocity like this there, they are mutually perpendicular. Then we take as BVL, induced EMF formula BLV, but here we cannot take the BH, we have to take the BV. BV perpendicular to L, perpendicular to V, right? Then BV value here we got 4 by root 3 into 10 to the power of minus 4 into BL, L is 30 into velocity 450. Right now we have to simplify this, and then you will get the answer. Okay, and now this is the induced EMF across the wings. And now my question is that one homework I am giving, right? And then how to simplify this, how to solve this homework. Okay, look at here. This you can simplify. Okay, you can simplify and answer volt. And I think you will get, I will give the answer also, that you will check whether you are getting or not, right? And here we are getting the 3.12 volts, 3.12 volt. Once you can check it. And here in this case what happening, aircraft of length in this solution, you see here it was very simple. Aircraft wing length is 40 meters and it is moving east side. For example, this side west means this side east will be there. It is aircraft with velocity they gave us 1080 km per hour. You can convert this into meter per second. How? You know already. You can multiply with 5 by 18, or otherwise you can multiply, kilometer is 1000 meters, hour is 3600 seconds. You will get in meter per second. Then after that here it is moving in the northern hemisphere where the vertical component of the earth magnetic field, the vertical component is they gave directly in this, right, 10 to the power of minus 5 Tesla. They are asking the induced EMF across the wing, right, across the tip of wings. This induced EMF formula here we can use directly, right? That formula is BVLV. Why? B suffix V, this one, B suffix V, not B into V. B suffix V means vertical component of the field. BLV is the formula, but in place of BH, BV, earth magnetic field, BH is there, BV is there. But in that BH, if aeroplane wing is this one, this is going this side, east side. Aeroplane wing and velocity are perpendicular. But if you take the horizontal component and velocity same direction, it will be there. Horizontal component of earth magnetic field, we don't take that one. We have to find out the vertical component. But in this question directly they give the vertical component, then directly we can substitute. But in this they gave the horizontal component, then for that we find out the vertical component by using angle of dip formula. This formula is there in the magnetism and matter, right? And this formula is there in electromagnetic induction. Okay, you can simplify it and you can write its answer in the comment. Okay, right. Thank you for watching my lectures. Subscribe my channel and share to your friends. If you have any doubt, you can contact me in the WhatsApp or in the comment box you can write your doubt.